The hidden world beneath our feet. A new world has been discovered, home to an unfathomable number of organisms that thrive in the most extreme and hostile conditions imaginable. These beings exist in absolute darkness, crushed under the immense weight of mountains, deprived of oxygen, exposed to searing heat, and bathed in acid, salt, or radiation. Yet, against all odds, they persist for thousands, perhaps even millions of years. Surprisingly, this world is not located in the depths of space, but rather beneath our very feet, within the crust of the Earth. This is the deep biosphere, a realm so recently uncovered that it feels as though humanity only learned of its existence yesterday. Its vastness is staggering, encompassing a volume at least twice the size of all the Earth's oceans combined, and harboring more microorganisms than the rest of the planet's surface. The total biomass of these subterranean life forms is estimated to be over 20 times greater than that of all humans, livestock, and wildlife combined. As we descend into this mysterious and perilous world, we enter an environment where the traditional rules of life no longer seem to apply. Life in the deep appears to be nearly omnipresent, thriving beneath the oceans, near volcanic vents, under the glaciers of Antarctica, and even beneath the landscapes where humans live and build their civilizations. To explore this hidden realm, we employ specialized drilling equipment to penetrate the Earth's layers, beginning with familiar territory, the soil. This uppermost layer of the Earth, where plants grow and animals roam, can be likened to the outermost skin of an onion. Soil is a dynamic and fertile environment, a complex mixture of air, water, minerals, and organic matter continuously bathed in solar energy. Life flourishes here in a state of abundance. Plants, the primary producers in this ecosystem, harness the energy of the sun to generate biomass at an astonishing rate, producing more than 30 times the total biomass of all Earth's animals annually in an endless cycle of growth and decay. However, only a minuscule portion of this organic matter is buried and preserved beneath the surface, providing a crucial resource that has sustained life for nearly 500 million years. As we dig deeper, we encounter an environment where most of the air has been compressed out, and we cross the water table into a zone saturated with groundwater, rich in minerals and traces of organic material. Here, the deepest reaching roots of ambitious plants struggle to extract nutrients, while scavenging organisms feed on the remnants of decayed matter. This underground layer remains cold, still influenced by the lingering effects of the last ice age. Further down, we reach the bedrock, the dense, solid foundation upon which all other layers rest. This layer, though seemingly impermeable, is riddled with fractures and water-filled pockets, and it can be found at varying depths, sometimes exposed at the surface and sometimes buried beneath hundreds of meters of sediment. Within this seemingly lifeless rock lies an entirely different world. As we drill deeper, the temperature steadily rises and the pressure intensifies. At a depth of 400 meters, the pressure matches that of Venus's surface. At 1,000 meters, deeper than the height of the tallest skyscraper, oxygen becomes nearly non-existent, and the heat reaches around 30 degrees Celsius. As we continue to bore into the Earth, descending nearly 4 kilometers beneath the surface, we are enveloped by rock exerting pressures comparable to those found at the bottom of the Mariana Trench. Temperatures here average around 120 degrees Celsius, though they can soar even higher near pockets of magma. This searing heat is a remnant from Earth's formation and the decay of radioactive elements like uranium and thorium, which bombard the crust with radiation. To add to the inhospitable conditions, some of the surrounding rock is permeated with extreme concentrations of salt. This environment seems uninhabitable, yet life endures. If we examine the rock up close, we see that it is not entirely solid. Instead, it is interwoven with microscopic pores, cracks, and voids. Certain rock types, such as sandstone, limestone, and basalt, are so porous that nearly 40% of their volume consists of empty space. Even denser formations like granite are riddled with tiny fractures. This extensive network of microcaves forms an uncharted world teeming with water and resilient microorganisms. These underground cavities are in constant motion, much like the atmosphere above ground. Subterranean mountain ranges shift and grind against one another, reshaping the landscape over millennia. Continents collide with the energy of millions of nuclear explosions, yet this process occurs at a pace as slow as the growth of human fingernails. Countless earthquakes, both minor and significant, rupture the bedrock, forming new pathways for life while sealing off others permanently. Within this ever-changing geological crucible, minerals are forged, organic molecules are synthesized and decomposed, and new opportunities arise for any organism capable of enduring the harsh conditions. The deep biosphere is home to some of the most extreme life forms known to science. These microorganisms, numbering in the octillions, have adapted to their nightmarish environment in remarkable ways. Some, such as Desulfuruda's Audax viata, function as self-sustaining ecosystems, deriving energy by extracting carbon and sulfur from the surrounding rock. In times of extreme hardship, they employ a remarkable survival strategy. They enclose themselves within a tough protective spore, effectively shutting down until conditions improve, sometimes remaining dormant for thousands of years. Other deep-dwelling microbes prefer company, forming complex communities such as the archaea known as Altiaceum hammerconexum. These organisms possess unique double membranes and produce nanoscale grappling hooks that allow them to anchor themselves to their surroundings. Some microbes form cooperative networks known as biofilms, where each member specializes in a specific function. Some consume methane and expel electrons, which are then absorbed by neighboring microbes that transform sulfate into sulfite. Others metabolize iron or utilize electrical charges to convert nitrogen and carbon dioxide into biomass. Life in the deep biosphere has found ways to exploit substances that would be toxic to most organisms, transforming them into sources of energy. However, survival remains an immense challenge. Resources are scarce, and energy is difficult to obtain. To cope with these limitations, some microorganisms adopt an extraordinarily slow metabolism, allowing them to live for centuries, or possibly even millions of years. These organisms consume so little that they may still be digesting nutrients they acquired at the time of a human's birth. They remain in a near-dormant state, conserving energy until an unexpected influx of resources enables them to reproduce. In some cases, deep underground habitats are large enough to accommodate multicellular organisms. Scientists have discovered asexual worms living kilometers beneath the surface, preying upon bacteria. Other predators, such as rotifers and arthropods, also hunt within these extreme environments. Despite these fascinating discoveries, much about the deep biosphere remains a mystery. The sheer depth of these ecosystems makes them incredibly difficult to study. Drilling risks contaminating samples with surface microbes, while laboratory conditions struggle to replicate the extreme pressures, temperatures and chemical environments found underground. Furthermore, because these organisms live at such slow metabolic rates, observing their activity in real time is a significant challenge. Most of what is known about them comes from genetic analysis, which provides insights into their potential capabilities, such as metabolizing methane or breathing nitrogen. This hidden biosphere represents one of the final frontiers of scientific exploration. Most of what we know has been uncovered in just the past 2 decades, and there is still much more to learn. Understanding these resilient life forms could have profound implications for medicine, energy production, climate science, and even the search for extraterrestrial life. If life can thrive deep within Earth's crust, independent of sunlight and conventional sources of energy, could similar biospheres exist elsewhere in the universe? Some scientists speculate that underground ecosystems may exist on other planets or moons, sustained by internal heat and chemical energy. There may be as many as 10 such environments within our own solar system, concealed beneath the frozen surfaces of seemingly lifeless worlds. As we continue to explore the mysteries beneath our feet, we may inadvertently unlock the secrets of life beyond Earth.